Welcome to all of you in this 40 lecture course on the artificial neural networks and applications. The subject of artificial neural networks has matured to a great extent over the past few years, and especially with the advent of very high performance computing, the subject has assumed a tremendous significance and has got a very big application potential in very recent years. Now, this subject of artificial neural networks is going to be covered in approximately 40 lectures, and in that today I am going to begin with the introduction to the artificial neural networks. So we will be first defining what a neural network basically means, and as the name implies, actually the term neural networks derives its origin from the human brain or the human nervous system, which consists of a massively large parallel interconnection of a large number of neurons, and that achieves different tasks, different perceptual tasks, recognition tasks, etc., in an amazingly small amount of time, okay, even as compared to today's very high performance computers. So this is what we are going to, this is what inspired the researchers to think that is there any way whereby a computer can be made to mimic the large amount of interconnections and the networking, okay, that exists between all the nerve cells. Okay, can it be utilized to do some complex processing tasks where today's high performance computers also cannot do? So this subject is the one that we are going to address. So today we are going to study the introduction to neural networks. That is going to be the topic of today. And specifically we are going to address the introduction to artificial neural networks. Now whenever I say artificial, okay, the question that immediately comes to our mind is that what is then the natural neural network? Okay. Now we know that our brain, the human brain, is having a highly complex and non-linear parallel computer. Human brain has a highly complex, nonlinear and parallel computer, and this can organize its constituent structural elements. So its structural constituents of human brain, they are known as neurons, and the neurons are interconnected not in a very simple way but in a rather complex way, so complex that many of the things we do not know yet. Okay, say if we have got a large number of such neurons or nerve cells, okay, which carry out the processing, they will be interconnected typically in a highly complex manner, okay, between each other, okay, and there will be connections which exist from one neuron to the other, and that is how a network is realized, okay, and this network is, as told, it's highly complex as well as non-linear, and is massively parallel, okay, because our human brain has got typically billions of nerve cells, okay, with trillions of such interconnections existing, okay. Now let us understand something which we could give as an example. Let's say a familiar task of recognition. Whenever we meet a person, okay, a person who is known to us, we can recognize that what's the name of that person, because he must be a friend of ours, he must be some known person, and we will be able to tell that who he is whenever we meet him. And how is it that we are going to do it? We are going to perform a task of recognition. Now we may be knowing thousands of people around, okay, what we have to do is to immediately, instantly recognize that person, that okay, he is somebody whom I had met 5 years ago, and his name is such and such, he works in such and such place, or I had met him in connection with these works, okay. We can immediately have this recognition task, okay, this face recognition. Now supposing instead of myself doing it, I ask a computer to do this task, how much of time would you think that a conventional computer is going to take? It's not going to be a very easy computation for a computer, because firstly that you know that person, but the computer doesn't know that person. Firstly that you have to teach to the computer that okay, there are photographs of different people, okay, supposing if I know 1,000 persons, okay, then I should be feeding the photographs of 1,000 people, okay, into the computer. Now I meet a person, okay, so I now capture his photograph, okay, and then I feed to the computer that okay, now you try to match the present photograph with all the 1,000 photographs that you are going to have in the database. Now the computer is meticulously do that task, okay, you must have trained him, okay, that how to perform a recognition, how to match the given image with that of the stored photographs, okay. And then ultimately at the end of all the computations and at the end of all the comparisons with 1,000 people's photograph which is there in the computer database, the computer is going to give us a result saying that okay, the person best resembles this photograph, okay. Now this could take quite a long time, okay, maybe a few hours, or who knows, maybe several hours. That would all depend upon how many such images are we having in our database. If our database is very large, okay, if we want to track down a person from a collection of, let's say, 10,000 images, 100,000 images, then the task is going to be really complex, because then so many comparisons are involved. But how much of time are we taking? We are doing it almost instantly. Now how are we going to do that very instantly? Is it that the computational capability that exists in the humans, okay, is it enormously different from the way a computer is doing? Well, if we try to think in terms of the processing speed, okay, we will be getting a different type of a result. Like today's silicon ICs, we know, okay, its response time is expressed in terms of nanoseconds. A nanosecond is time which is 10 to the power minus 9 of seconds. Whereas if we are looking at the processing speed of a human neuron, okay, that may be 5 to 6 orders slower than that of typical ICs, okay, and that may take several milliseconds, and milliseconds, as you know, is 10 to the power minus 3 seconds. So it is 6 order slower, 5 to 6 order of slower. But in that case, the question remains as a very puzzling one, that then how is it that the neural processing within the human brain, okay, happens to be much faster than that of today's computer, because we are using, I mean, the elementary block of the digital computation is all those integrated circuits which have got processing times of the order of nanoseconds, whereas the elementary block of the human computation, the neurons, that is 10 to the power minus 3 seconds. So then how is it that this one happens to be much faster than this? The answer lies in the fact that the network of human neurons in the brain, okay, that is massively parallel, okay. There is a massively parallel network of neurons. And as I told you that the number is of the order of something like 10 billion. Typically there will be 10 billion of such nerve cells or neurons, and this will consist of approximately 60 trillions of interconnections. So the answer lies in this massively parallel structure, okay. So now the question is that, is it possible for anybody to perform the tasks that a human brain does? Is it possible to mimic that using the using the electronic components, or is it possible to realize that task using a computer software? Well, it's not that easy, because we do not have, even in the age of parallel computers, we cannot really think of putting so many processing units and realizing it in a massively parallel scale, okay. All that we can do within our limitation is that we can interconnect a network of processors, no doubt, and rather than considering the structure of a human brain in totality, okay, we can only try to mimic, okay, a very small part of it, an extremely small part of it, okay, in order to do some very specific task, okay. That's the best thing that we can do using the using electronic components, and using the software we can do only to a limited extent. We can make neurons, okay, but that is surely going to be different from the biological neurons that we have talked about so far, okay. So what we are going to study is the artificial neural networks, okay. By artificial, we inherently mean that something which is different from that of the natural or the biological neurons. So this is the subject, artificial neural networks. In short form, we very often refer to it as ANN, okay. Now, firstly, that let us understand that why at all we are going in for an artificial neural networks, okay. What are the advantages that it is going to offer to us, okay. So let us list out its usefulness and some capabilities. Number one, that it exploits the non-linearity. Now, I think all of you should be able to understand the terms linearity and non-linearity. Basically, if there is a system, okay, where we give a set of inputs and we expect some output out of it, in that case we call the system to be linear if the relation between the output and the input can be best described in terms of a simple linear equation. If there are, let us say, 4 inputs and 1 output, then if the output is a linear combination of all the 4 inputs, then naturally the system is linear. Whereas if we if we can write the output only in terms of not only the linear terms, okay, but also its higher order terms, in that case the system is no longer linear, the system becomes non-linear. Okay. Now, lot of times for simplicity we consider linear computational models, but if we are looking at the real life problems, most of the real life problems, they happen to be highly non-linear in nature. So, for that purpose we need non-linear computational units as well, and the neurons are the ones that happen to be non-linear. So, what we have got here is an interconnection of non-linear neurons. So, in artificial neural networks we have got an interconnection of non-linear neurons. And another thing which should be noted is that the non-linearity is distributed throughout. In fact, the very nature of computation, as you can realize, is highly distributed in nature. So, the non-linearity that we are talking of is naturally distributed. The second usefulness that one must talk about is the input-output mapping. You see that you are providing some input to the system, and in response you are going to get some output. Okay. Now, I mean, we can go in for a learning mechanism, a learning where a teacher is involved, in which case what we do is that we feed the inputs and then we also say what the expected output is going to be. So, in other words, we are specifying that for a given input what is going to be the output or the desired response. Now, it is possible that our computational unit that we are having, that is not able to achieve the actual output that we get may be different from that of the desired output. Okay. There may be a difference between what is actual and what is desired. What we can do is that we can accordingly modify, I mean, if our system has got a set of free parameters, some parameters that we can adjust. So, if we are having such kind of free parameters, then we should be able to adjust the free parameters of the system, okay, such that for a given input or a set of inputs, we can obtain the output that is closest to our desired output. Okay. In that case, we may not be able to achieve that immediately. Okay. First time we feed a pattern, okay, our system doesn't know, hasn't encountered that pattern before. we are feeding that, okay, what the desired response is going to be, but then the actual output will be different. So, the difference that exists between the actual output and the desired output, that adjusts the parameter of the system such that the difference between the actual and the desired is minimized, and that we may have to do several times. So, there is a process of learning, okay, and this learning, as you can understand, involves a teacher. There is a teacher who says that corresponding to this input, this is what the output should be, and if it is not, then the teacher is asking you to correct. The teacher is asking you to adjust the free parameters which are available in the system, so that next time you feed the input, the same input, you can get an output which should be closer to that of the desired. So, this is something which is very important, very, very important, okay, and this is what is going to make the neural network, okay, remarkably different from the conventional computational unit, and that is in the sense that it has got a learning ability, okay. And in this case, the input output mapping that we were referring to so long is basically referring to learning with a teacher, okay. Here a teacher is definitely monitoring. Now, not that all the time we can find a teacher, okay. There may be some situations, okay, where we may have to learn without a teacher also, maybe from simple associations. You see, let us look at the developmental process of a child. Now, a child is born with a brain, and that brain has got, I mean, a massive interconnection of its neural processing units, but a child has to develop himself or herself, okay, with a process of learning, okay. A child sees so many new things. I mean, when the world is new to a child, the child learns, the child finds out many things by himself or herself, okay, and that the child is able to do through some process of association. Let us say that, I mean, a child sees so many animals, okay, around. Now, a child sees that a group of four-legged animals is called a cat, a group of four-legged animals is called a dog, okay. Now, a child may be making mistake initially. I mean, sometimes, okay, a child could get confused between what a dog is and what a cat is, okay. So, he may feel little confused, but the parents are there as his or her teacher, and the parent corrects that, okay, no, this is not a cat, this is a dog that you are pointing to. So, now the child knows that, okay, a dog has got some specific pattern characteristics, a cat has got some specific characteristics. So, when he sees more number of cats and he sees more number of dogs, then it is possible for the child to distinguish that, okay, this category of four-legged animals are cats and this category of four-legged animals are dogs, okay. Now, a lot of times a child learns by himself, okay, I mean, through associations, okay. He makes mistakes, he explores a lot of things on his own, he makes mistakes, he corrects. So, learning, we have got two types of learning, learning with a teacher and learning without a teacher, or a sort of auto-association that takes place. Now, the third thing that one has to talk about the characteristics of the neural networks is what is called as adaptivity, okay. Now, the neural networks, they can adapt their free parameters to changes in the surrounding environment. So, these can adapt the free parameters. In fact, I mean, some of you may be feeling little confused that what exactly do I mean by the word free parameters. Okay. I will come to that later on. Actually, in respect of the human brain, the free parameter basically refers to what is called as the synaptic connection, and it all is tuned by the strength of the connections, but we will come to that later on. So, at the moment, let us accept this word free parameter, okay, where the explanation of that would come little later, or if it is not clear through this lecture, naturally with the next few lectures you will be able to automatically understand this. Okay. Now, this can adapt the free parameters, okay, to the changes in the surrounding environment. Well, you see, I mean, naturally, you can understand one thing, that we definitely have to go through the process of learning throughout our life, okay, in some sense or the other. Now, the world that was there during our childhood, okay, is not the same world that we are seeing today. There are so many changes, okay, so much of developments have taken place in the scientific and technological world. Our lifestyle changed altogether, okay. Our culture has gone through changes, okay. There are changes everywhere, okay, and you see that still we are able to cope up with this world. Now, how is it so? So, there are so much of changes in the surrounding environment that we are seeing around us, but we can adapt ourselves, okay. That is a capability which we the human beings are having, okay, and that we are doing by making some internal adjustments or the adjustments of the free parameters that we will come to a little later. Another characteristics of the neural networks is that it not only gives us the response. Now, response I was referring to, basically what I said was that there is some kind of, when I was talking of the input to output mapping, okay, there is a definite input that we are feeding and we are expecting some response, okay, or the output from it. Now, at the end of learning, okay, it is able to get the correct response, but a neural network can not only report what the response is, but it can also tell that it is the response with what confidence level. So, in that we can say that the neural network is able to give what is called as evidential response, okay. And just see that I mean, we the human beings, okay, lot of times we give the response with some evidentiality in it. Like, we can always say that, yes, I think it is going to happen that way. We associate the word I think. That means to say that we are associating some kind of a confidence measure, okay. Not that we are 100% confident, but maybe when we say I think, with a good degree of confidence, we can say that yes, the feeling is that it's going to happen. So, that is to say associating a confidence with the decision. So, it is not only a decision, but it is a decision with a confidence measure, with a measure of confidence. So, all this we are telling as the characteristics of the biological neural network systems. Okay. Now, whether all these things could be mimicked into the artificial neural networks or not is something that we have to explore later on. Okay. Another very important characteristics which the biological neural network system exhibits is that its ability for fault tolerance. Now, what happens if, supposing, one particular nerve cell is malfunctioning, or let us say that one connection, okay, from one nerve cell to the other, a single connection is somehow not working. Okay. Is it so that our entire nervous system is going to collapse because of that? No. We can still carry on with our normal activities without any noticeable change. Okay. If too many neurons are affected, maybe that we will have some effect, okay, of it, but okay, I mean, it is not something that is leading to a catastrophic failure. Whereas, I mean, unless you built in some fault tolerance into the computer system, okay, you know that unless that is purposefully built in, then, I mean, the failure of one processing unit could very often lead to a disaster. The entire computer system can collapse, or the entire network can collapse. I mean, this sort of catastrophes can happen, whereas with the biological neural networks, okay, if some neuron malfunctions or if some connections are malfunctioning, okay, all that it leads to is some kind of a degradation in the performance, certainly not a catastrophic failure, and that degradation is what is called as graceful degradation. So, graceful degradation in the sense that it all depends that how much of fault has taken place. If the fault is too many, then the degree of degradation is large, whereas if the fault is not much, then the degree of degradation is small. So, it is called as the graceful degradation, okay, and in that sense the biological neural network system is highly fault tolerant, okay, and it is possible to incorporate this fault tolerance mechanism even in the artificial neural networks also. The next point that we must point out, okay, in fact this is this is motivated by the fact that there is a massively parallel computation that our brain is doing. Now, if we have to list about the capabilities of an artificial neural networks, okay, then for the artificial neurons we can list one of its characteristic, that the neurons, the artificial neurons, that should be VLSI implementable. So, we can tell about its VLSI implementability. Okay. By this, what I mean to say is that using the very large scale integrated circuit, it is possible to integrate a large number of neurons together. Now, naturally, we cannot think of integrating 10 billions of neurons. If we could do that, then we could have mimicked the human brain completely, but we cannot do that much. But as I was telling you, that if it is utilizing a network of artificial neurons, okay, to do some particular task, okay, some particular application, then naturally, I mean, we could be able to do that, okay, using the VLSI implementation, and in fact, it is possible that way because the neurons are absolutely parallel computational unit. Now, the neurons which are existing in a system, which are forming a network, they can all do independent computation, okay. I mean, it is, one is of course dependent upon the others, but there is a large number of parallelism. I mean, there is a good degree of parallelism that is involved with it, and in fact, when we see the particular neuron structures, okay, in the subsequent lectures, okay, this aspect will be more and more clear to us, okay. And then coming to the basic motivation of the artificial neurons, okay, another point that we should say is its neurobiological analogy. Now, everything, as I was telling you, was motivated by the biological neural network system. Okay. So, these 7 points, okay, are basically dealing with the properties of neurons, but all these properties, okay, could be imparted to the artificial neurons as well. Okay. They are the properties which the biological neurons fulfill, and they are the properties which the artificial neural networks also can be made to fulfill, starting from the aspect of nonlinearity, the input-output mapping or the learning mechanism, the adaptability. Okay. The adaptability is a thing which we can do, but even an artificial neuron also can be made adaptive, okay, if we train it that way. Then coming to the evidential response, there also we can train a neural network, artificial neural network to do that. The fault tolerance, the VLSI implementation, and primarily that everything is biologically, neurobiologically motivated. Now, we should, I mean, before going into the depth of the artificial neural network, okay, we should see the structure of the human brain. Okay. Now, rather than drawing a human brain, okay, we will be considering a typical nerve cell, okay, which we refer to as a pyramidal cell, okay, and that should look something like this. Let us say that, okay, now here we draw what is called as a cell body. So, supposing this is the cell body, and with that we now connect the following. We connect a thing which is called as axon, okay, and these axons are basically acting like transmission lines, the lines that can carry electrical signals, okay. And in terms of its electrical characteristics, one can say that it is having a high degree of electrical resistance and offers a large capacitance, okay. So, this has got high R and high C. Now, these axons, they act as the transmission lines for carrying the electrical signals, and they end up with the, so here you can see that there is some tree like structure, okay, and all these ultimately end up in synaptic terminals, what is called as synaptic terminals, and these are basically used for making connections with the other nerve cells, okay. Now, this basically is nothing but the output part of the neuron, okay. I should have shown the input part first, but let us draw that. Now, these are the response zone, that is to say with the synaptic connections, and that will lead to the other neurons. And then we have here this is referring to the receptive zone, and we call this as basal dendrite, okay, which is basically referring to the receptive zones from which we can get the inputs, okay. So, these are the basal dendrite, and then we have the apical dendrites. In fact, as compared to the axons, the dendrites are having more number of branches. Okay. Whereas dendrites are much smaller as compared to axons. Now, typically these lengths, the lengths of axons are much larger than that of the dendrites. So, these are the apical dendrites, and this ultimately would be connected to the synaptic inputs. So, these are all going to synaptic inputs so that it can receive signals from the other neurons. So, you see that this is the complete what is called as the pyramidal cell. So, now the pyramidal cell as shown here, this can receive synaptic inputs from other neurons, okay, and these will basically carry the signal all to the cell body. Okay. So, here the processing part will be done where all these inputs will be combined, and how they are going to be combined? They will be combined in accordance with the strengths of these connections. Now, all the connections are not of the same strength. Some connections are very strong and some connections are weak. Now, if the connections happen to be very strong, in that case the signals also, the signal strength also will be large there. Like here, if this connection is strong, then the signal that will be contributed by this input will be much more than if this happens to be a weak synaptic link. In that case, the signal coming from here will be weaker, the signal from this may be weaker. So, like that, the strength of the synaptic connections will decide that ultimately what signal, what is the net signal that will come to the cell body as the net input. Okay. Now, that will ultimately decide that what the response is going to be, and the response will be transmitted through the synaptic terminals to the other neurons. So, it has got a set of inputs, this is also connected to a set of outputs, because ultimately this is one pyramidal cell which is considered, okay, within a very large, massively parallel network of neurons. Okay. Now, as I was referring to the free parameters sometimes back, the free parameter essentially refers to the strengths of these synapses. Now, as I was telling you that every input is associated with some synaptic strengths, its connection strength. Now, supposing, okay, initially there is some a priori connection strengths that one can take, and then accordingly there will be some response, and that response could be different from that of what is desired. So, if the actual response is different from that of the desired, naturally we have to adjust the internal parameters of the nerve cell. And what is that internal parameter? It is this strengths of the synaptic connections. So, what we do is that we now alter the connection strengths, and then we feed the same inputs, okay, and find out that what the output is going to be. This time we may be closer to that of the desired, but still we may not be exactly equal to the desired, so that it will go through another round of synaptic strength modifications, and this could go on iteratively till the actual response is close to that of the desired response. We may not be able to achieve exactly, but may be able to achieve close to that. So, the synaptic strengths are basically dictating that what the signal strength is going to be, and these are basically acting as a free parameter to our biological nerve cell processing. And equivalently in the artificial neural network, then we should be building up something, some electrical equivalent of such synaptic strengths. Okay. In fact, in an equivalent electrical model, we can represent a neuron like this, that a neuron or a nerve cell will be connected to several inputs. Let us say that these are the inputs, and it will be again connected to one or more than one outputs, and these inputs will be connected to the nerve cell through some strengths of connection, and we may be indicating the strengths of the connection. Okay. Right on top of this arrow, we can write down that what is the strength of this connection. Let us say the strength of this connection we call as W1, the strength of this connection we call as W2, this as W3, and supposing there are n number of such inputs connected, and we call this strength as Wn. And we are having here the input signal available to be that of x1. Here the input signal that is available, let us say it is x2, here x3 is available as input, and here xn is available as input. So here what happens is that the net signal that will be available at this neuron is going to be x1 into W1 plus x2 into W2 plus x3 into W3 plus so on up to xn into Wn. There are n number of such neurons that is interconnected. So this unit will be summing up all these responses. But then this is a linear summation, but ultimately do we want a linear summation? No. We must be wanting some decision out of it, that whether yes or no, or a decision which is, more quantifiable. We don't want this computation alone. So in order to arrive at a decision, this must be followed up by some nonlinear processing unit. Okay. There must be some nonlinear unit that will follow this summation. Okay. And effectively the output that will be available at the output of that nonlinear unit, whatever we have, is going to be our output of the neuron. Okay. Now, if that output is different from that of what is desired out of it, then what we have to do? We have to simply change the strengths of this connection. We have to change W1, W2, W3 up to Wn, so that with this same set of inputs, with the input still remaining at x1, x2 up to xn, we can then obtain an output that is close to the desired response. Okay. So this is the equivalent model. So this is the biological model of a nerve cell, okay, with its inputs and outputs, and this is the equivalent electrical model. In fact, we will be considering such equivalent electrical models of artificial neurons, okay, in our course. Now, we give you an idea about what we are going to study in this course. So, our lecture series will be divided into some specific modules. So, as the course content, we can say that we will first begin with the models of artificial neurons. Okay, that's what we are going to cover from the next day, models of artificial neurons. And then we are going to consider the learning mechanism, the different mechanisms of learning, the supervised learning, the unsupervised learnings, okay, the different conditions for learning, the auto associations, and all these things we will be seeing in this chapter. And then we will come to what is called as the single layer perceptrons. In the single layer perceptron, what we will be doing is that we will be considering a network of neurons where we will be having the neurons organized as just a single layer. So, we will be having the inputs, then we will be having a layer of neurons, and then we will be having the outputs, and the layer that is available is a single layer. Whereas this idea is later on extended to achieve what is called as the multi-layer perceptron, where other than the input and the output, okay, we are going to have some intermediate layers of processing. Okay. So, that is the realization of multi-layer perceptron, which we will see. In fact, we will be seeing that the single layer perceptron models have got a lot of limitations, and those limitations can be overcome using the multi-layer perceptrons. Then after studying the multi-layer perceptrons, where one can use the multi-layer perceptrons to solve what is known as the problems which are not linearly separable, they can be solved using multi-layer perceptron, and they can also be solved using what is called as the radial basis function networks. That also we are going to cover in this lecture series. And then we are going to study what is known as the principal component analysis, okay, which is based on the eigenvalue decomposition technique, and we will see that how a neural network can be very effectively utilized to perform the eigenvalue decomposition and to project given data into the eigenspace, okay, for the purpose of dimensionality reduction. And then we will come to a class of unsupervised or self-organizing networks, okay, which is called as the self-organizing map. So, this will be under the scope of our study in the lecture series. So, that is all for today, and from the next class we will begin with the artificial neuron model. Thank you very much.